This is the AMP Centre Tower in Sydney in 2010. And this is the same tower today. It represents the gold standard in sustainable building design because, well, the greenest building is the one that's already built. Retrofitting or upcycling a skyscraper is a way to make a new building from old without the need to demolish the existing structure. During its reconstruction, the newly named Quay Quarter Tower reused 65% of the existing structure and 95% of the original core, saving 12,000 tonnes in embodied carbon. That's equivalent to 35,000 flights between Sydney and Melbourne. It also took just 4 years to complete construction work. But the partial demolishing and reconstruction of an established building is no easy engineering feat, to say the least. And despite the success of Quay Quarter's transformation, that's not to say the same could be done for any arbitrary building. Now, before we get into some of the more detailed engineering challenges that had to be overcome, let's take a deeper dive into what actual changes were made to the building. It's safe to say that the philosophy and innovation around vertical living has seen a lot of progress in recent decades. The redesign of Quay Quarter has completely transformed the architecture of the building and has created new spaces in line with these shifting ideas around urban living. Whilst most of the existing core was kept, the north side was stripped down to allow an outwards extension to be built on. The extension is split into 5 different volumes which spiral up the height of the building. This was an intentional decision made not just for aesthetic purposes, but rather to offer each section optimal views over areas of interest. The lower floors face the busy metropolitan streets below, whilst the top floors have shifted their view eastward over the famous Sydney Opera House and Royal Botanic Gardens. The choice to split the building up like this extends beyond just offering the occupants better views though. The designers wanted to achieve a vertical village concept, with each volume acting as its own self-contained community. Unlike the building's once uniform internals, each volume has the floors arranged around an open atrium and connected by a spiralling staircase. The goal was to create a visual connection between each level while simultaneously creating communal areas for people to interact. The way these volumes have been stacked has further opened up outdoor terraces underneath each, making outdoor space more available to the people living inside. Whilst my point here is to highlight how creative and innovative thinking has been possible on a constrained canvas, there is still significant environmental reasoning behind these decisions too. The rotated volumes themselves help shade the northern side of the building from the evening sun, whilst the new facade covering the entire surface of the building blocks up to 30% of the solar radiance. These passive shading methods improve energy efficiency and reduce mechanical loads on the building simultaneously. And a modernised building, of course, means that you have to have modern elevators. What about some double-decker ones, in fact? During the renovation, 31 new elevators were installed, 18 of them with the capacity to serve 2 floors at the same time. Passengers at the base board on different floors depending on whether they are going to odd or even numbered levels, increasing capacity without the need for extra lift shafts. Integrating these modern elevator systems into the existing shafts proved to be a challenge though, and required some of the lift infrastructure to be custom built. Now, the concept of upcycling a skyscraper at the face of it sounds pretty simple, but when you start to think about partially demolishing a skyscraper and then stitching a whole new structure to it, it's really nothing short of remarkable. At the time the deconstruction began, the Quay Quarter Tower was both the tallest demolition task and largest scaffolding undertaking in the world. So how does one go about a project of this nature? Well, the first answer is a whole lot of testing. And there were really 2 problems the building's structural engineers were dealing with. Not only did they have to make sure the existing building was structurally sound in accordance with modern construction codes, they also had to account for how the new and existing structures would interact with each other once they were joined. This meant considering time-dependent changes like shrinkage, which happens as the concrete dries, and a process known as creep as the material experiences loading over time. These These differential movements between parts of the structure would prove to be one of the greatest design challenges. To effectively model and predict these interactions, a detailed model of the entire building, both new and old, was made using finite element analysis. But how do you model the properties of 50-year-old concrete? In the end, it meant taking over 3,000 core samples, along with other non-destructive methods to gain insights into what they were playing with. No model was perfect though, and in order to test its accuracy, a whole array of instruments were placed on the building to take measurements in real time. These included tilt sensors, accelerometers, and strain gauges, allowing the model to be continuously calibrated to align with the current state of the building. Now, any parts of the building highlighted by this model to be under strength had to be retrofitted to ensure the safety of the building. This was done through a mixture of techniques such as the steel jacketing of columns to raise their compressive strength and carbon fibre installations to strengthen members in tension. The latter here was of particular concern, as the new cantilever design on the north side, combined with the wind forces, induced tensile forces on the south-facing side of the building. Now, we haven't yet discussed how the new part of the building was actually fixed to the existing structure. It came down to using over 2,000 steel anchors, which were drilled and then chemically fixed into the original core, and then connected to the steel reinforcements of the new core. Now remember, we also talked about the differential movement of the two structures. To allow for the shrinkage of concrete in the new section, the designers left what is known as a pore strip between sections. This is basically where a section of concrete slab is left open to allow the concrete to settle on either side before it's then later filled in to complete the structure. This, combined with the use of low shrinkage concrete, helped mitigate large shear stresses. Another final design decision that was made was the installation of a tuned mass damper at the top of the building following testing. It's essentially a counterweight that moves in the opposite direction of the building's sway, reducing the movement and making the building more stable. All this clever engineering and extending of the building eventually resulted in both a doubling of floor space and human capacity when the project finally reached its completion in 2022. The building has since won multiple awards, including the 2022 World Architecture Festival Award for Building of the Year and the International High Rise Award for 2022 to 2023. The engineers behind Quay Quarter had done something never seen before, but that begs the question, can we expect to see similar projects now following suit? It's hard to argue against the benefits of adaptive reuse, not least because of the significant material and project savings it offers, but it might not be applicable to every skyscraper in the world today. This is the HSBC headquarters in Canary Wharf, or at least it is for now. With post-pandemic norms seeing more and more people working hybrid jobs, the demand for huge towers filled with office space is in rapid decline. Companies like HSBC are now choosing to downscale, something that will leave many skyscrapers like this one empty, and in most cases destined for demolition. But amid London's housing crisis, there are increasing arguments to be made for converting these office buildings to living space, saving the building in the process. The question is then, is this realistic? A recent article by Bloomberg UK highlighted some of the issues such a transformation might face. The problem, perhaps obviously, lies in the fact that buildings like these have been designed to be offices and not apartments. A building like the HSBC Tower has a problem of size, and I don't mean size in terms of its height, but rather in terms of its depth. Buildings designed to house open-plan offices can afford to have large floor areas, as the light from the outer windows is able to travel right through to the centre of the building. Once you start adding in dividing walls though, you start to get this prison cell effect of rooms isolated from sources of natural light. Now there are ways to work around this, for example by recessing the windows into each floor. Other more complex solutions involve creating large atria for light to filter directly into the centre of the building, albeit at huge monetary and design costs. Then you also have the problem of rerouting the internal ventilation systems to supply multiple different spaces as opposed to one open floor. Now whilst these are all design challenges that can probably be overcome, it's clear that conversions like these are going to require a lot of out-of-the-box thinking from those who decide to undertake them. Quay Quarter Tower has proved the concept, but now it's up to others to follow. With ever-growing urban populations, the skyscraper is inevitably here to stay. The question is, how many new ones will we have to build? I'm Luke, and this was the upshift.